Hello everybody, in this video we're going to be discussing when you should use OLLCP. In case you do not know what OLLCP is, it's basically a set of algorithms that forces an edge-only PLL, okay? So what you do is you'll do your OLL, but at the same time it's also going to permute your corners, and this will force an edge-only PLL. So that means you can only end up with a U, Z, or H perm or even a skip, and it increases your chances of getting a PLL skip from 1 in 72 to 1 in 12. So today we're basically going to be discussing when this should be used. Now first off, why wouldn't this be used in a solve? Because if you wanted to get an edges-only PLL, wouldn't you want to do that every time? Well, that is wrong, okay? There are a lot of cases where the algorithm to permute the corners is so long compared to the standard cut OLL that it's faster to actually just do the regular OLL and then do the PLL you get from there. But in this video, I'm going to be showing you how to figure out which cases you should use OLLCP and which ones you should just stick to the standard OLL. Now, there's a few things we need to take into consideration here, okay? So we need to take into consideration how long it takes you to do each algorithm, the OLL algorithm and the OLLCP algorithm, okay? So then you want to take the average of time in terms of how long it takes you to do each of the cases you could end up with and figure out what that is. That will in turn give you your average PLL time when you get it. And then we'll use those numbers to put it together. Alright, these equations here will help calculate your average if you're unsure how to do it. So, starting out with the solved ones, okay, this is where your corner is solved, or all your corners are solved. So, you want to take the UA perm, multiply it by 4, and then you also want to take the UB perm, multiply it by 4, add those two together, take the Z perm, multiply it by 2, and add that to that, and then take the H perm time and add that to that, and then divide all that by 12, and that will give you your average. And then for the adjacent swap ones, too many to write out, so I'm just going to say that you have to take all the individual times, so that means every single G perm, all the A perms, and so on, each individual one, not just one of those. Add those times together and divide that by 12. Then for the diagonal swaps, you want to take the V perm time, multiply it by 4, and then the Y perm time multiplied by 4, add those together, add the two N perm times together, and then take the E perm time and multiply that by 2 and add those together and divide it by 12. So, this will give you all the different types of PLLs, because when we're doing OLLCP, we're predicting the PLL that we're going to get. So instead of it being all 21 cases, you're narrowing it down to just a few select cases. So now to calculate which one is faster. So, starting out with OLLCP, we need to determine how long it would take if you did that route, okay? So, the C there stands for how long the OLLCP algorithm will take, and the E stands for how long the PLL will take average-wise, okay? So, we need to figure out how long that would take average-wise, and then when we go over to OLL and PLL, we need to figure out how long that would take average-wise. So, the O stands for the cut OLL, so the standard one you'd use instead, and then the PLL that you would get. Now, you have to figure out which PLL you're going to get, whether it's corner solved, adjacent swap, or diag swap, so we're taking that into consideration. Take the average that you calculated from that, and then you need to figure out which one takes the least amount of time, so that one would be less than the other one. Once you figure out that one, that will tell you the route you should take. So you should be able to calculate which route would be faster. However, if you have a case that's going to force a diag swap and doing the algorithm to force the edge-only PL out is way too much work, another potential option that you could take is finding an OLLCP that forces an adjacent swap. If you do that, you have many more algorithms that would work, okay? Because there's 4 different types of results that are still theoretically good, okay? And you can use whichever one is faster to figure that out. So if you're going to go that route, you need to take into consideration the same thing, except instead of figuring out how long it would take you to do the EP algorithm, you want to figure out how long it would take you to do the adjacent swap algorithm. And if one of those is faster, then you should definitely choose that route. So taking this a step further, you can also simplify your PLLs even better than this, okay? So, as you know, OLLCP will also give you a better chance of having a PLL skip, and if you use the last method where you determine if the CP is worth it, sometimes you may miss out on getting a PLL skip, okay? So what you can also do instead is you can memorize the different cases and figure out which ones will give you skips or at least really nice PLLs. And you can also use this to avoid bad PLLs if you know you're going to get one. However, this is going to require you to learn more recognition, and you have to kind of essentially learn one look last layer cases and then memorize the OLL and PLL for them. But what that would also do is it'll also help you predict completely which PLL it is, and you can jump right into it. So I got two examples here. So we have this here, and if we do the OLLCP here, we end up with a PLL skip like this, okay? And if we did it with this one, we'd end up with a U-perm instead. However, if we do the standard OLL, we get it with a nice J-perm, which is really quick. And the extra work that we'd have to do to avoid that and force an edge-only PLL is probably not worth it in that case, because you can do the standard OLL, and then the J-perm is just so fast already. So that's another thing you can do, and this would also help you to decrease your last layer time on a lot of cases, because you know the cube a bit more, you can jump into it quicker, and you can force the good PLLs and avoid the bad ones much more often. So this method I showed you in figuring out which method is faster can also be applied to a few other things. This can also be applied to figuring out which method for any part of the cube would be faster if you chose that route. For instance, if we did PLL before OLL and that's the way we solved the cube, we could determine which route would be faster. So we'd have to take all the different outcomes of the cases and figure out average-wise which one would be faster. And you might also be wondering, why isn't this used for VLS in determining whether it's better to just insert the pair and then do the OLLCP? Well, here's the answer. So this affects two steps, but VLS, it's essentially skipping the whole step, okay? And when you insert a pair and then do an OLL, you're technically doing the VLS. So I don't know the VLS for this case here, but when I insert it and get a fat tune like this and do that, I'm technically doing VLS that way. But the whole point of VLS is to skip OLL by canceling into it, because if you already have a pair out like this, and then you insert it, you'd be taking it out again and then inserting it like this. So essentially VLS is you're starting in the middle of OLL and you're continuing it on. But a lot of them do require you to insert it first, or at least in a different way. And because OLLCP does not guarantee a PLL skip in every solve, that's why this method is needed. Because when we calculate this, we need to take into consideration every possible outcome of the step that we're doing and the one that it's going to affect. So I hope this video was helpful for you guys. Let me know what you guys think, and hopefully this helps you figure out which OLLCPs you need to learn and which ones you don't need to. And I hope this helps your time. So thank you guys for watching, and I'll see you guys on my next video.